another meeting that unfortunately, I don't know how I got like 70 people in one meeting, 76 in another.
Okay.
So I'm going to revert those people back over to you, but I'm going to go ahead and introduce you now and let you go ahead on and start your presentation. So I apologize for this. So
No problem.
alrighty, so we're going to get all your audience in attendance here in just a second. Okay, so without further ado, we have Dr. Matthew that's going to share with us today. So Dr. Matthew Jones leads Hazen and Sawyer Stormwater Practice Group and offers national expertise in the full life cycle of stormwater control design, implementation, maintenance, and performance monitoring. He has played a key role in a wide array of stormwater efforts, including innovative green infrastructure initiatives in Boston, New York, Philadelphia, and Washington, D.C. His efforts include developing solutions with green infrastructure and other stormwater controls to address CSO reduction, water quality improvement, drainage relief, and climate resiliency. Thank you, Matthew, so much for taking your time out with us today. And without further ado, you have the floor, and I'm going to revert all those other people back to you.
Sounds good. Thank you, Michelle.
Thank you.
And yeah, really happy to be with you all today and talking about this topic. And without any further delay, we'll go ahead and jump right in. So first, I wanted to kind of give some overall context, and I think it's somewhat nice the way these presentations have sequenced out. Last month, Dr. Barbara Dahl gave a presentation on nature-based solutions for mitigating flooding in eastern North Carolina. And I think you'll find as we go through, there are some parallels, but also some key differences that I wanted to kind of speak to right here at the start. In really two main areas. One, Barbara presented on kind of a broad array of nature-based solutions. For this presentation today, going to be focusing a bit more narrowly on urban green stormwater infrastructure. And then similarly, the nature of the storms that we're going to be focusing on are a bit different as well. Whereas Barbara was talking about some really infrequent large-scale flood events, on the order of a 100-year event, we're going to be focusing a bit more on things in the neighborhood of the 10-year storm event. So I hope you find that it builds on the topic there nicely, but did wanted to thank Barbara for a great presentation and provide some context as we get underway with things today. So a few things in terms of background context. One is that I think we've all seen both within North Carolina and throughout the country, green stormwater infrastructure becoming more popular and prevalent. And so in the context we're talking about here, when we're talking green stormwater infrastructure, it's things like right-of-way bioretention areas or kind of various means of distributed bioretention. It's permeable pavement. Those types of practices, again, more kind of smaller scale distributed green stormwater infrastructure throughout the environment, and less kind of large scale nature-based solutions like water farming and things of that nature. But we are seeing green infrastructure becoming more popular and prevalent for a variety of reasons, a lot of co-benefits it provides, and increasing preferences for its use as a stormwater management tool. While we've seen that kind of growth in popularity, it's also important to note that storms are changing and the characteristics of those storms are changing. And we'll get into a good bit more detail on that. But something that we were running into more and more are questions about how do these two phenomena intersect or collide. I know I've told this story. I'm a big green infrastructure proponent, but I always cringe a little bit where there's a headline and a newscast of a major widespread flood event. Hurricane Harvey comes to mind, dropping on the order of 40 some inches, and I remember someone saying, well, this is why we need more green infrastructure. Well, that is really kind of part of what we wanted to explore here is, does green infrastructure have a role amidst these changing storms, and what might that role be? And that's a real important question because a lot of priorities, both within North Carolina and more broadly in the national context, are changing. And that's something that's specific to green infrastructure. We've seen a lot of changes in interest. North Carolina has a long history of green infrastructure implementation through a lot of the leadership work of DEQ and NC State and others, encouraging, providing the resources and encouraging implementation of fire retention and other green stormwater infrastructure practices going back many years. Nationally, there's a lot of implementation within CSO communities for MS4 drivers. And in some contexts, exploring the use of green infrastructure for drainage and climate resiliency is a bit of a newer development and funneled by these changing priorities that we see. And here's just one illustration of that. This is not a scientific poll, but was a few months ago given a
Hey,
presentation.
Matthew.
Yes.
I'm so sorry. Let me interrupt you. I see there's a couple of people that has their mic on. So could you please mute your mic? This is making it very hard for everybody to understand Matthew. I'm so sorry to interrupt, but I do.
Yeah, no problem.
That
Yeah,
can
no,
be
thanks,
very
Michelle.
irritating. So
Hopefully that's better. Feel free to stop me again if not. So this was just to kind of help illustrate that issue. Given a presentation on master planning up in Virginia. So important context here. This is Chesapeake Bay watershed. Water quality improvement, nutrient load reduction is a major focus. We asked two questions, about 40 to 50 people in attendance that responded to this poll. What is your top priority for stormwater improvements? And you can see here, 60% said flooding and drainage relief, even within a state that has, major regulatory programs focused on water quality. Water quality also a significant portion, but also important over on the right is, almost everybody was balancing multiple priorities. So again, this increases the importance and the relevance of understanding what role might green infrastructure have in the context of changing storms and changing priorities as it relates to flooding and drainage relief. So with those changing storms, one of the things that we want to understand is how are those storms changing? And so we have a tool that we put together a number of years ago to help kind of answer that question. We regularly get the question of, that seems like a real major storm event. Is that normal or not? And so this tool does some analysis. It feeds in real rainfall data and then breaks those out into storm events, compares it to Atlas 14, and generally says, are these storms happening more frequently or less frequently than we would expect, or that Atlas 14 would suggest occurs on average? And so this is what that looks like for a few locations in North Carolina. So a few things, you see different storm durations across the top, ranging from a 2-hour to a 24-hour duration, and then recurrence interval down here. And so, for example, here in Raleigh, for a 6-hour duration, 1-year storm, we would expect on average, this is looking at 8 years of rainfall data, or 7 years rather, 7 1-year 6-hour storms, we saw 8. And so you can see that there are some departures there when we compare to that Atlas 14. Some departures, by nature of statistics, some departures are not altogether surprising, particularly when we're looking at something on the order of a 7 to 10 year time frame. But we do see some differences there. Here in Charlotte, across the longer durations, pretty much in line with the Atlas 14 expectations. For the shorter durations, we do see some departures with some larger events. And then in Wilmington, we see some departures. And one of the things that's particularly notable is we see some departures from what Atlas 14 would suggest for our 1 and 2 year storms. So this is indicating that over, in this case, the past 12 years, we were seeing a little bit more of an increased frequency of 1 and 2 year storms than we would generally expect. Now, one of the things, and there'll be several things we'll kind of touch on here that is notable when we talk about green stormwater infrastructure in the context we're focusing on here today. I'm talking about in the context of stormwater controls that are designed to manage the water quality storm. So in the neighborhood of an inch to 1.25 inches throughout our state. So that's not the 10-year storm event, but that is closer to some of these more frequent storms that we're having. It's also notable when we talk about what are the public's interests. These 1 and 2 year storm events can certainly cause nuisance drainage issues that the public would like to see addressed. And so this is giving some early indications that that green infrastructure may have some role in managing these more frequent storms where we're seeing some departures from our historical norms. So that's looking in the past, and that phenomena of seeing some departure, particularly for those frequent events, is not uncommon. We've kind of run that analysis in a number of cities throughout the country, and that's a somewhat common finding of seeing that departure. But again, that's looking backwards over recent history. What about looking forward into the future? So there are a variety of climate models and tools to assist us in this analysis. Here's a plot showing projected average daily maximum temperatures for Wake County into the future. I'm not focusing so much on temperatures in this presentation today, but it does help illustrate some important concepts. One is that we have these different emission scenarios that we're looking at. Not worth getting into all the details of that, but there's a lower and a higher emission scenario that are often a focus, and those are represented by the blue and red here. The other point is that, or another point, is that there are a number of different models that inform this type of analysis. I think the Climate Resiliency Toolkit, which is presenting this, or this particular tool, presents results from somewhere on the order of 30 global circulation models that are downscaled and made relevant at a scale suitable for what we can look at here on like a county level. So you see some bands of potential outcomes, and then those bands, not unlike slightly different context, but not unlike in hurricane season when we're looking at storm tracks and we look out days in advance, that band widens out. Somewhat similar phenomena here. As we get further out in time, we can see a clear trend of increasing temperatures, but that band and that uncertainty grows as we get farther out into time. So that uncertainty is an important concept as we get into some things later. Now, part of the reason that I showed temperature here is that these models generally are better able to represent and project temperature changes than they are something like storm events, and particularly the design storms that we're kind of interested on from an engineering standpoint, because there are a number of additional factors in play that affect those storm size and frequencies. But we do have some tools that allow us to look at that and approximate that. One is there's a tool, a SWIM climate adjustment tool, that pulls in downscaled climate data, and for a given location, you can see in different recurrence interval storm, you can see what projected change in that design storm depth is projected. So in the context here, you've got different scenarios, different time frames. To simplify some things here, pull in a high and a low estimate. When we look across North Carolina, you can see, so here, this is for a 10-year, 24-hour design storm. So much of what we're talking about here today is focused on that particular storm because that's a common target for drainage design and stormwater conveyance design. We're looking at a 2045 to 2074 timeframe. So here's our current 10-year, 24-hour design storm for these different cities throughout the state, and then a low and a high projected adjustment to that design storm depth, and what that means in terms of real storm depths. So you can see on the low end, those storms are projected to stay relatively the same. On the high end, on the order of 5 to 6% increase, which translates to something less than a half an inch of depth increase. Now, it's important to note here that there are a variety of ways of kind of evaluating this climate data and coming up with different results. One of the things it doesn't cover North Carolina, but there was a recent study in the Chesapeake Bay watershed looking at potential changes to design storms throughout the Bay watershed. That particular study found that those adjustments range anywhere from in the neighborhood similar to these, little change to 5-6%, all the way up to getting into kind of a 20% increase for those 10-year design storms. But even with that kind of an increase, we're still talking about lower depths in the context of our common green infrastructure sizing that is looking at a 1-inch storm event. So how are storms changing? There's an increased frequency of smaller storms in many locations that could contribute to nuisance flooding when compared to kind of our historical norms. And we see incremental increases in our 10-year storm depths. Again, depending upon what analysis you look at or what data you're referencing, you can get into some different results. But I'm not aware for something like a 10-year storm, any projections, certainly not for North Carolina, that talk about kind of doubling of these storm sizes or increases of that magnitude. We're talking about incremental increases. So that brings us back to the question of what is the role of green stormwater infrastructure amidst these changing storms? And really two sub-questions as part of that. One, can GSI mitigate incremental increases in storm depth associated with climate change? And two, can it play a larger role in managing localized urban flooding? So beyond the competing priorities or changing priorities and competing priorities we discussed earlier, there would certainly be some benefits if green infrastructure can serve a valuable role here. One of those is limitations of conventional pipe upsizing. This is something we're doing a lot of work in some of the ultra urban areas in the country where, putting in a larger pipe network and carrying that to the receiving water is not a practical option because of the intensity of development and a variety of other constraints. And so in those cases, that's part of what we're looking at is what can green infrastructure do in those circumstances. The other gets to some broader implications for sustainability, community disruption, and that sort of thing. When we talk about pipe replacement, and spoiler alert, and we'll talk about this at the end, but the point of this is not to say that there's no further need for pipe replacement. That's going to continue to be a key tool in our toolbox here. But talk about pipe replacement, that can often be a disruptive activity. Digging up a roadway, has community impacts associated with that. When we think about from a sustainability standpoint, not done a specific life cycle analysis, but you can certainly imagine the impacts in terms of greenhouse gas emissions and other sustainability factors of, excavating a material, disposing of that, replacing it with a new material. Again, an important tool, but pipe replacement can be disruptive. Green infrastructure can bring its own disruption, but it would certainly provide some benefits if it could be a tool in our toolbox to help offset some of these increased storm sizes and effectively prolong the life of our buried infrastructure and delay the need to upsize some of that conveyance infrastructure. So that was one of the key questions that we wanted to consider and why we were kind of contemplating this question. Beyond looking at some of the kind of high level comparisons of changing storm sizes and that sort of thing, we wanted to get into the hydrology. So we did that looking at a generic curbside bioretention, like you see illustrated in the figure to the side here. It was sized to store runoff from a 1-inch storm event. We assumed a soil infiltration rate of a half inch per hour. And then we routed a 10-year, 24-hour NRCS hydrograph through that facility. We accounted for both the current standard, in this case we used a 4.9-inch, which I think is for Raleigh and one other, but representative of a North Carolina storm, and a 6% increase for that future climate scenario. Routed the flow through the bioretention, accounting for any bypass and overflow. We looked at existing and future conditions with and without GSI, so a total of 4 scenarios. And then the fundamental test that we were applying is if the peak flow for our future condition with green infrastructure is less than the existing condition without green infrastructure, then we effectively mitigated those changes associated with climate change and changing storm characteristics. So our first scenario that we looked at is basic bioretention. Water flows in through a curb cut, gathers in a shallow surface depression, infiltrates into underlying bioretention soil, and if the capacity is exceeded, it's spilling out and continuing down the roadway. So here's the results. There's going to be a sequence kind of following this pattern. So we've got the sizing target, some of these other features we'll talk about in a moment, the storm. Again, all this is focused on the 10-year, 24-hour storm. And here's our hydrograph, time across the bottom, flow here. And these are our peak flows. So without green infrastructure, under current circumstances, got a peak flow of 6.5 CFS per acre. With green infrastructure, under the current climate, knocks that down a couple tenths of a CFS. As we'd expect, under the future climate scenario with a larger storm event, we see higher flows. And in this case, we're not fully offsetting that. In fact, we see a 5% increase from the existing condition. And you can kind of see what happens here. So when you look at our hydrograph, what's happening is this surface depression is filling up at the beginning of the storm event, and then the movement of water into the bioretention soil in the context of our 10-year storm event, larger storm than we would typically expect our bioretention to manage, it exceeds that capacity. We do get a small reduction in peak, and that's really tied directly to the amount of water moving into the soil at that point in time. So we look at at this particular scenario, the green infrastructure capacity was exceeded well before the storm peak. We get that marginal peak reduction attributed to the direct effects of infiltration. You see that both in the current and future conditions, and this did not pass our test for mitigating impacts of changing storms. So as a green infrastructure proponent, I'm not very excited at the moment. But unfortunately, we have a lot of options and design tools that we can apply that may help with this. And it's important to note that a lot of these tools are not necessarily new. They may be new being implemented in this context of trying to use green infrastructure to provide drainage relief. But many of them, in fact, all of the ones that we'll be talking about here today, are used with some regularity in CSO programs to maximize the volume capture of stormwater with green infrastructure. So the first tool that we want to look at here is incorporating an internal overflow. So that could take a variety of different forms. We can have a stone gabion that's providing a connection between the surface and the stone bed. We could have a perforated riser. Here's an example. Here, well, both of these, perforated riser inlet connected to a perforated distribution pipe. So here's an example of the latter. We've got a vertical pipe here that connects into a distribution pipe within the subgrade of this bioretention. It's raised just a couple inches above the surface. It's got a grate on it, which is removed in this context. And then from a maintenance standpoint, we've got a screen that fits down inside that to catch anything that's coming in and we don't want solids to get down into our distribution pipe at the base of the bioretention. But really the purpose is that before we get overflow that's bypassing our system altogether, try to make the most use of the storage volume that we have. It's worth noting that in doing this, we are exchanging some water quality treatment for storage capacity. That water that is going down directly into the subsurface is not getting the same level of treatment as the water that's infiltrating through our bioretention soil. We try to mitigate that in some circumstances, as you can see from this photo here. This riser is elevated a couple inches above the surface, so we do allow for encourage that some of that first flush, at least some portion of that first flush, to infiltrate through the bioretention soil, but provide another mechanism for water getting into the system. So when we look at implementing that design modification, we start to get a little more promising results. You can see we're using more of our storage, really filling up the void space that we have. But for this 10-year storm, that void space and that storage is still exceeded before the peak of the storm arrives. So in terms of helping us from a conveyance standpoint, what we're sizing there for the peaks, really no change from our basic bioretention. So the next design modification that we're looking at is, again, also something that's used with some regularity in CSO programs, is a slow release orifice or some kind of flow restriction on our underdrain. So that can be a cap with a drilled orifice. Here's an example of the Philadelphia Water Department detail that includes the flow restriction in that manner. It can be a weir wall with some kind of orifice plate or other flow restriction in that weir wall. So this is a schematic of use for some larger green infrastructure designs implemented in parks and other areas. But the concept, is the same here, even at the kind of smaller scale we're talking about. It could be a valve that's restricting that underdrain flow, or even an automated valve that's regulating the flow out of that bioretention. For the purposes of this scenario here, what we're looking at is we adjusted that underdrain flow restriction to maximize storage within our bioretention for the 10-year event. And here are the results when we do that. So a huge benefit, I should note, the prior examples we were looking at did not have an underdrain at all. If we had an unrestricted underdrain, it's not necessarily providing a lot of help because we're not necessarily holding water in the system. But with this regulated underdrain, again, we're able to kind of maximize our storage to coincide with that peak of the storm. And so you can see here that during the early parts of the storm where we're not as concerned, we're not exhausting our storage capacity. We're able to allow some of that flow to continue downstream, and then able to provide that reduction at the peak of the storm. So you can see here when we look at our scenarios, in this case, when we compare our current without GSI to our future with green infrastructure, we do provide a 10% reduction from existing. So more than making up for the changes that we're seeing associated with changing storm characteristics in the future. I mentioned the automated valve could be an option here, and that in particular could be beneficial. As I said, we did static sizing of an orifice to maximize storage for this 10-year 24-hour, but with an automated control, you could change the storage characteristics to optimize the storage for whatever storm is occurring or is projected to occur for a particular installation. So when we look at this, our scenario summary, we're getting flow regulated throughout the storm, substantial peak reduction, and we are mitigating those impacts for changing storm events. We also want to look at what other options that we have. One of those options is like to call iceberg green infrastructure. So in general, we're talking about a larger green infrastructure, a larger bioretention. In this particular case, looking to man it for a 2-inch storm target. I mentioned the iceberg green infrastructure because many times in an urban or developed environment, you may need that type of an approach. You may not have adequate storage surface space, but you can distribute a larger subsurface footprint to provide some of that storage that we're focused on. So in this scenario, retaining the internal overflow and the controlled underdrain, you can see we see a substantial reduction in peaks, which is not surprising given that larger storage volume. And then the last scenario that I wanted to speak to is this concept of a gutted bioretention. So as a green infrastructure engineer, this may sound somewhat of something like a horror movie, taking our nice bioretention and stripping of it of all the things that make it a bioretention area in many respects. So in general, kind of looking at a responsive repurposing of bioretention to maximize the storage that we're providing and to support drainage relief. So removing those treatment elements like the bioretention soil, perhaps even the stone, and really doing whatever we can to maximize storage within the footprint, whether that's using just stone in place of soil, or including different HDPE chambers or grid structures to maximize that void space. So this is truly a case where we're, really reducing the water quality benefits, but really trying to prioritize drainage relief and capture. And part of where this may come into play is the potential to retrofit a facility near the end of its functional life. Or, we talked about the shifting priorities that we have seen, but thinking about in future instances how green infrastructure may operate if drainage relief and flooding becomes a major priority. And one of the things we've seen in some other areas is within a watershed, maybe there are other means of addressing and supporting some of the water quality goals. So looking at a retrofit near the end of that functional life, you may have to look at replacing that facility anyways to maximize that storage space. And so in this case, we're sticking with that 1-inch green infrastructure sizing target, but by stripping out all of those treatment elements, we increase the porosity, the effective porosity of the system quite a bit. And you can see by doing that, even without resizing to be able to occupy a larger footprint, we're able to realize some substantial reductions, a 78% reduction in this particular case from that existing condition. So when we look across the summary of scenarios that we're looking at, our basic bioretention or incorporation of just the internal overflow doesn't really have a meaningful impact in terms of mitigating climate impacts. But when we layer that on with some of these other adjustments that we're talking about, we can see anywhere from marginal to substantial reductions in our peak flows, even beyond those that are projected for future climate conditions. And again, I noted earlier for this scenario in terms of the design storm adjustments, we were using a 6% adjustment, so a fairly nominal adjustment. But with some of these other things, if we're able to reduce, in the neighborhood of 50% or more, we've got some potential capacity to mitigate even larger adjustments if those projections change in the future. So back to our question, can GSI mitigate incremental increases in storm depth associated with climate change, and can it play a larger role in managing localized urbanized flooding? The answer to both of those questions is yes, but as Bill Hunt, my friend and advisor, often says, it depends. Part of the toolbox, but it depends upon a number of site specifics. So our gray infrastructure is not dead yet. It's not going away. as I said earlier, is certainly an important, will continue to be an important and really the predominant approach for addressing drainage issues, both existing drainage issues and those associated with future increased events. And that's for several reasons. One, and what we're looking at here, the green infrastructure is not addressing the entirety of the storms. We're focused more on kind of mitigating those changes or those increases in storm depths. And another thing is just logistics of, where we're putting in these features with controlled underdrains. Those underdrains obviously have to have a drainage network that they're connected into, and that sort of thing. So I want to be clear that this, the takeaway from here is not, we don't need pipes anymore. We need mostly green infrastructure. There are some other factors in play as well. One of those is siting constraints. We talked about siting constraints or limitations to implement upsized pipe infrastructure, but green infrastructure certainly has siting constraints as well. So, for the routing exercises we were looking at, we were assuming that we could route flow to our green infrastructure and we had capacity to manage it. But that may not always be the case. So when we start to scale things up and look at a watershed scale, and again, this is something that there's a lot of experience with, particularly through CSO programs that, through consent decrees are really trying to maximize their implementation. We've got some good context for, what degree of implementation may be practical within an urban area. And also localized hydraulics vary quite a bit. In some cases, providing the detention that green infrastructure would provide can provide a lot of great value. And other specific local hydraulic circumstances may diminish the benefit. So it does require some site-specific analysis to arrive at some conclusions there. But it's also important to note. So those are some of the kind of limitations. It's important to note that especially amidst changing priorities, increasingly, stormwater controls can't do just one thing. And so we try to look across the full array of what is the role of this green infrastructure, both now and in the future, and consider that as we're underway with planning, design, and implementation efforts. And increasingly, we're seeing a lot of incorporation of multi-function stormwater management areas. And I think that's going to be a real valuable tool in our toolbox as we look at how do we mitigate the effects of changing storm events. Where can we incorporate more storage, more detention in a distributed fashion throughout our urban environment through things like modified bike lanes and parking lanes. The examples that we talked about here focused on bioretention, but the same underlying concepts apply to perennial pavement and other green infrastructure approaches. Here's another example. This is some work that we're doing up in Queens in New York at a public housing facility, looking at a variety of tools. How can we distribute green infrastructure and stormwater controls throughout the site and do it in ways that provide multiple functions? One of my favorite examples of that, completed the design and it'll be going into construction soon, is a basketball court. Underneath the basketball court is a subsurface retention system with chambers and voids to help kind of filter the runoff and provide some storage for smaller events. But during the larger events, these cloudburst events, providing the court itself is depressed and provides direct stormwater storage. So really thinking about how can we get the most storage and make the best use of the space that we have available to us in the urban environment. And really, one of the big takeaways, back to this fundamental question of what is the role of green infrastructure amidst changing storms and the flooding concerns that we're seeing, it's really about building a bigger toolbox. Some of those tools are going to be tried and true approaches that we've used for decades. Others are going to be newer approaches, whether it's green infrastructure or tying in adaptive and real-time controls, or even doing those things all in concert with each other. It's increasingly going to be important to have a bigger toolbox available to us. And I think the work that we've done has shown that green infrastructure does have a seat at the table. It is not a silver bullet solution. I know we all wish we had one, for the stormwater concerns that we face, but definitely can have a meaningful role. And the other important point, and what I'll close on, is it fits with the broader approach of building adaptability for the future. So this is my son at a Cub Scout event this past weekend. They were building Lego race cars. And I think the Legos are kind of a good analogy for our stormwater toolbox. We need to think about, in this particular case, they had a set of Legos, they were building cars, and they kept rearranging the Legos to see kind of how those cars would work. We can think about that same adaptability when we talk about our green infrastructure implementation in this context. And it's whether it's kind of at one end of the spectrum, looking at a gutted bioretention, or incorporating a controlled underdrain, something that maybe at the start of implementation we cap that underdrain altogether, really maximize the infiltration, the volume retention that we're getting. We've got that adaptability in the future so that we can release flow, provide better peak flow reduction, and even that orifice, that flow restriction itself, is something that can change over time. Where we are implementing this part of our construction documents, we'll go ahead and have the contractor fabricate several different flow restrictions so that those can be swapped in and out over time as is needed to adjust the performance of that infrastructure. So again, having that broader toolbox and having the opportunity to build an adaptability is really going to be essential for our stormwater management efforts into the future amidst the anticipated changes and the uncertainty in the magnitude of those changes. So with that, I really appreciate everyone's attention here this morning and happy to answer any questions, both during the session here. I think we've got some time before the top of the hour, and also you're more than welcome to reach out to me by email with any questions, additional questions.
Okay, Matthew, we do have a couple of questions here. One of them, I think Mike wanted to know, what type of maintenance does GSI typically require?
Yeah, so Mike, that's a great question. So, and it's an important one, particularly for some of these design features. So when we talk about our kind of typical green infrastructure, a lot of drainage type maintenance, making sure our inlets are clear, curb cuts are clear, overflows are clear. There's a vegetation maintenance and that sort of thing, a variety of kind of your typical green infrastructure maintenance. With the things that we're talking about here, some of these adaptations have some unique maintenance implications. I touched on one with the internal overflow, or sometimes called like an enhanced infiltration riser. With our typical standard bioretention, a lot of the fines, particulates, pollutants for that matter, are captured near the surface. So that can make maintenance easier because by removing the first several inches of bioretention soil and replacing it, we can remove a lot of that. If we're tying in some of these features to send water more readily into the subsurface, that changes a bit of the context for what does that look like in terms of long-term maintenance. So typically that includes more consideration of pre-treatment before water gets into those surface layers. I showed one example of kind of the screen that fits within that riser to help capture some of the debris and solids. It also may change the nature of how often or whether you need to kind of use a vac truck or a jet to clean out your underdrain. The same is also true of those flow restrictions on the underdrains. Again, that's something that's a lot of experience implementing that in the context of CSO programs. But that is a factor in the design. One of the things with those flow restrictions, try to configure it in such a way that you could remove the restriction in the dry. So let's say it's in the context of a threaded cap, you remove that threaded cap, what may be a relatively small orifice is now opened up to the full diameter of that pipe. So any debris and all that may be blocking that orifice can flush out of the system. But there are certainly some unique maintenance considerations, but all things that can be addressed.
Okay, I have another question for you. All right, so Francine wants to know, would you say that gutted viral retention is essentially gray infrastructure? If not, what makes it green?
Yeah, so that's a great question. It's certainly uh and somewhere it gets into the a bit of the semantics of it, I guess. I would say you're certainly stripping out a lot of the water quality benefits of green infrastructure. Though you are still retaining some of those benefits. If you've got an open bottom, you are presumably still getting infiltration into the underlying soils, and you're getting volume reduction benefits and treatment benefits through that. And the example I showed here was a bit of an extreme example, but it is something that you could tailor. A good example of that is setting the under drain or the outlet for that type of a structure with some storage depth above the bottom, so that you're getting have a volume that you're dedicating more towards infiltration. So there are some trade-offs. I think it's debatable whether that's still green infrastructure or not. Certainly, you would expect less water quality benefit than with a standard bioretention, but the primary, I guess, reason for showing that was not so much advocating implementation of that type of a setup now, although it would have some benefit if you're limited in what gray infrastructure you can implement in terms of pipe infrastructure and all, but more thinking about future adaptability. We've not done that to this point. Had a bioretention that we kind of stripped out, but I will say that comes up more and more often in conversations when we're doing especially kind of widespread green infrastructure implementation. If our priorities change down the road, how might that work, or how might that be done, or what might the implications be? So definitely becoming part of the conversation and something to consider.
Okay. Okay, Matthew, I think that's all the questions that we have. So I am so sorry that we sent you guys the link on here for PDH credit. So what I'm going to do is, I'll take that back. I'm take that back. Dr. Jones, we do have another question
Okay,
from Nicholas as I'm kind of flipping through here. I'm so sorry about that.
no problem.
He said from the question and answer, many coastal towns in North Carolina must prioritize the water quality benefits of GSI and balance that with flooding mitigation. To make matters more challenging, these municipalities often rest on shallow water tables that limit the feasible depth and functionality of GSI projects. Do you have any recommendations for GSI tools or philosophies under these coastal conditions?
Yeah, that's a great question, and something that we do encounter. As you said, we've got um, a lot of constraints for green infrastructure implementation already, and then those can be exacerbated in coastal areas, particularly due to the shallow water table. So one of the things that we try to do in those circumstances um, pertains to the kind of the iceberg green infrastructure example that I showed. Really try to maximize the footprint of our practice, and in doing so, reduce the depth. And then, again, particularly in an urban environment, it's not common that you would have a lot of open surface space that you can make use of. But by extending that footprint under the roadway or under the sidewalk, can help provide more storage volume per unit depth, essentially, in those coastal environments.
Okay, so another question. At what point does the modeling define the margin of error on any of these projected increased stormwater depth? It looks like the observed increase could be within a margin of statistical insignificance. I know a lot of the climate modeling is incredibly inaccurate, especially looking out 50 to 100 years, as noted.
Yeah, so those are good questions. So there is some the the routing is fairly straightforward, but it's important to emphasize that this was a generic, intentionally a generic example, and it's hopefully mentioned earlier, it is going to vary somewhat depending upon localized hydraulics and things of that nature. A point that I meant to note, but didn't, so I'm glad you reminded me, is the increases, something like a 6% increase by itself may not necessitate needing to do anything. A relatively small adjustment in the context of the storms that we're talking about and the infrastructure that we're talking about. So you may have, for that magnitude of adjustment, you may have existing capacity within an existing design or existing installed infrastructure to manage that increase. But you may not as well. And I mean, that's certainly a common phenomenon that you have drainage infrastructure that is already undersized, and then changing storm characteristics add additional pressure to that. So that was really the focus of this, is trying to understand what tools are available to help mitigate some of those changes. And what we found is if we found that under the best circumstances, all we could do was get kind of a 5-6% flow reduction, I think that would change the overall utility of this approach. But what we found is that you could get substantially larger reductions that may have some meaningful impact in terms of delaying the need to mitigate or to upsize pipe infrastructure. As you noted, the determining with precision out into the future how design storms will change is there's an inherent uncertainty, and that's not a critique on the modeling efforts as much as just in any case where we're projecting future conditions, there is an inherent uncertainty, and trying to project the specifics of storm impacts based upon future climate scenarios is itself particularly challenging. And so that is also part of why having the broader toolbox, but having that adaptability becomes really important. And that's where I think green infrastructure has particular benefit. If you've implemented infrastructure, but find that through changing storm characteristics in the future, things that you're realizing, you need more capacity. Green infrastructure provides a modular kind of incremental means of implementation to provide some of that relief.
Okay, Matthew. Dr. Jones, I'm so sorry. I think we have pretty much got all the questions. I just want to go back here to make sure I didn't miss anyone. I think we've gotten everything. I just want to thank you, Dr. Jones, for taking your time out for helping us or for assisting us with this webinar. And so it seems as if everybody is enjoying based upon the comments in the chat, everybody really enjoyed your presentation. And I terribly apologize for some of you guys. I had to redirect back to the correct webinar. I have no idea what happened there. So I was running around here looking crazy for a hot second, but I'm glad you guys were able to join. I just wanted to remind you that we do have another webinar that's coming up on August the 17th, and that is going to be about rethinking bioretention with Ryan Winston from Ohio State University. So be looking out for the marketing materials on that. And for some of you, yes, the presentation that asked in the comments, the presentation will be available. We will have that uploaded on our website per usual.